Hello, my name is Juan Vargas Garcia. I study electrical mechanical engineer. My topic is about studying for deploying RFSoC technology for singing and radar applications. Definition: RFSoC single. RFSoC, this innovator PCIe character advance of the capabilities of the Gen 3 version of the ceiling are absorbed to be able to perform across the entire sub-6 GHz spectrum, which is a requirement for applications such as 5G LTE, fast array radar, and satellite communication.
Next generation RF communication systems need to reduce both footprint and power, while at the same time increasing the hardware flexibility to address a wide range of use cases or radio variants. Xilinx is integrating direct RF sampling converters into its MPSoC devices to create a new, all-programmable RFSoC family to address these challenges. In a moment, we will look at the performance of a recent 16nm FinFET test device. But first, let's review some of the benefits of direct RF sampling technology. Today's radios are typically implemented using analog signal processing techniques, similar to what's shown here. As we can see, the frequency shifting and selection is carried out in the analog domain, and the data converters operate at or near baseband. Some programmability can be added to these analog signal processing blocks. However, there are limits to what can be achieved in terms of flexibility and performance. But when we move the data converters closer to the antenna and carry out more of the frequency shifting and selection in the digital domain, we have a robust, highly flexible platform for radio implementation. With direct RF sampling converters, this is now possible, and we can take advantage of advanced CMOS technology to implement very power-efficient, programmable RF signal processing. Let's take a look at the converter performance which can be achieved in advanced 16nm FinFET technology using digitally assisted techniques. The board you're seeing here contains a 16nm FinFET test chip with both 4 gigasample per second RF sampling ADC and a 6 gigasample per second RF DAC. The converters were evaluated across process, temperature, and power supply variation, and the built-in calibration and digitally assisted techniques delivered industry-beating levels of performance. For example, here we're looking at the output of an RF DAC on an FSW spectrum analyzer from Rohde & Schwarz. Excellent performance was observed for the RF DAC, which here is generating two tones centered at approximately 1.9 GHz and separated by 20 MHz. The third order intermodulation distortion, or IM3, at minus 65 dBc illustrates very high linearity of the DAC. To test the ADC, a high-quality signal source, such as the SMW200A, also from Rohde & Schwarz, was used to synthesize both carrier wave and modulated waveforms. Additional analog filtering provided the signal purity required to evaluate the RF ADC. Data captured from the ADC was analyzed using FFTs implemented with LabVIEW software from National Instruments. Here we can see the FFT of a 1.9 GHz input tone sampled at 4 gigasamples per second. The second and third order distortion components are aliased in band to the first Nyquist zone, as indicated by the red colored markers on your screen. Other distortion components shown are interleaving artifacts, which are greatly suppressed by the built-in digital calibration. For more details regarding the performance of the RF sampling ADC and DAC shown here, please refer to two papers published at the Gigahertz Converter session at ISCC in February 2017. The integration of direct RF sampling converters with our 16nm MPSoC devices greatly increases the flexibility of the RF platform, while at the same time reducing footprint and power. Please visit Xilinx.com to understand more about the unique benefits of the all-programmable RF SoC.
Singer, signal intelligence. These four are intelligence collect analyzes information by interesting communication between people and between machine or device.
Signals Intelligence, SIGINT, Communications Intelligence, Common Training Course. Duration, 3 days. Signals Intelligence, SIGINT, Training Bootcamp is a 3-day training course, covering all angles of signals intelligence, SIGINT, including communications intelligence, COMINT, electronic intelligence, ELINT, and foreign instrumentation signals intelligence, FISINT. Advanced Network Characterization, ANC, Digital and Mobile Communication, DLMC, 4G, 5G, Wi-Fi, IAT, SATCOM, Radar, UHV, VHF, H, Microwave, Wave and optical signals using the most recent innovations and approaches in the SIGINT field are talked about. Target audience. SIGINT training course is designed for hardware and software engineers, analysts, scientists, project managers, military intelligence professionals, and anyone else who wants to learn about the SIGINT. Members will learn out about SIGINT and apparatuses to gather SIGINT from different sources, including outside correspondences, satellite, space, business correspondence frameworks, versatile systems, radar and other electronic and correspondence frameworks. The instructors will give you what to gather, and how to process, examine, produce, and disperse signals intelligence data and information for intelligence and counterintelligence purposes. Learning objectives. In the wake of finishing the SIGINT training boot camp, the members will talk about the fundamental and propelled SIGINT standards, talk about systems for defending SIGINT draws near, characterize the jobs and duties that help SIGINT situations, lead whole investigation between SIGINT pattern and best practices, get acquainted with RF hypothesis, clarify standards behind software-defined radio, SDR, and more. Course agenda and topics. SIGINT 101. Elements of SIGINT. The fundamentals of signal analysis. Signals intelligence, SIGINT, technical principles. SIGINT operational planning. Principles of collection. Principles of electronic intelligence. Advanced electronic intelligence. Workshops and case studies. Request more information regarding signals intelligence, SIGINT. Visit tonex.com for course and workshop detail.
Application in telecommunication. The RFSoC Bus Acquisition Card for Wireless Application RFS 8440 is ideal for 5G, LTE, fast array radar, and satellite communication projects.
Hi, I'm Peter Ibis with Bitware, here today to introduce you to our RFX 8440 PCIe data acquisition card. This card is built around the 3rd generation Zinc UltraScale Plus RFSoC from Xilinx, capable of addressing the entire sub-6 GHz spectrum, which, as you know, is a critical need for applications like 5G, LTE wireless, and phased array radar and satellite communications. It's got 4 channels of analog in and out, plus digital expansion ports for connecting to a number of other cards, processors, or storage. Let's take a closer look at the card, starting with the analog front end. You can see here on the front of the card the 4 inputs and 4 outputs, plus some connectors for clocks and triggers. The default configuration of the card has the electronics optimized for L-band, but other configurations are available. Let's take off the cover now. You can see the analog electronics include bypass connectors. This card has excellent signal sensitivity with up to 40 dB of low noise variable analog gain ahead of the digitizers, giving operators the ability to optimize dynamic range for the current input signal conditions. We've got more detail on the analog performance on the Bitware site, so be sure to request that. Now let's talk about the RFSoC chip. So this is the Gen 3 version, which means it's got 14-bit and 5 gigasamples per second on the input side and 14-bit and 10 gigasamples per second on the DACs. That's quite a lot of performance for such a small chip. And what we've done that's unique is enabled this on an enterprise class yet cost-effective PCIe card instead of more expensive platforms. So you're getting the performance that used to require quite a bit of additional analog circuitry than you see here, moving more of that RF design into the digital domain and still being able to acquire, process, and act on RF signals. A bit more about this Xilinx device. It's got a combination of programmable logic with 8 gigabytes of DDR4 and then 2 ARM devices, one dual core and a quad core with 16 gigabytes of dedicated DDR4. So it's a powerful chip that's really quite unique in its capability. Okay, let's talk about the digital domain. It's worth pointing out here that the hardware employs sophisticated clock management and control circuitry for single and multi-card synchronization. The RFX 8440 includes expansion options for versatility across a wide range of applications. Here on the back, you can see the 8-lane Oculink expansion port provides additional PCIe with Gen 4 support, NVMe storage, or dual 100 gigabit networking, allowing you to build flexible, scalable solutions with up to 200 gigabits per second of bandwidth. If you're doing any data capture or recording, be sure to look at our data capture and recorder reference designs, as we have some impressive IP available that's well suited to this solution. You could also connect another bitware card to bring further processing or connection options for your digital data. There's some other interfaces as well, including GPIO, DisplayPort, Ethernet, and USB. As for programming the RFX 8440 for specific uses, customers can develop applications with support from MathWorks tools. And one last benefit worth mentioning is that the RFX 8440 has the ability to operate standalone without the need for a host platform. If you're a customer who wants to deploy in a server or edge platform, then please consider ordering your RFX 8440 as a bitware TeraBox pre-integrated server. Thanks for watching. For more information, please contact us at bitware.com.
Pros and cons. Pros: massively more simple and speed RFSoC product design, connect and preserve into or RF at the gigabyte serial singles. General a 30 RFSoC power supply from and single pass 11B input. Include flash and DDR4 memory for FPGA and R processor. Maintenance PCB constraint for B-points, field and geometries. Excellent packs for a design SAC requirement. Cons: RF single input. 60. Analog are a single with gigahertz bandwidth, exporting digital signal pickout, crossing between analog channels, signal faults, index and impedance, gigabyte serial line, 28 GB GTE, signal packs, integrate and impedance, big all right consideration. Clock manager. Data converter simple close. FPGA, fabric and gigabit serial lines. Power supply requirements. RFSoC chip require 30 different power supplies. Analog supply boost the extreme client. In Ecuador. The Ministry of Telecommunications at the National Directorate of the Civil Register launched the temporary zone for this 5G technology in Ecuador. This state-of-the-art technology will allow the adoption of ACTs to massive internet service and ensure migration to high-speed network in the continental and insular territory. The objective of the implementation is to optimize results and improve the experience. Conclusion: RFSoC technology has revolutionized the FPGA chip landscape by including on-chip A, D, and GI functions and R processor. In addition to the already expanded FPGA and processing completely available for custom applications, this type of RFSoC FPGA solution offers a multi-kind data conversion and processing solution are on single chip. RFSoC offers a powerful and unique solution to address some of the most demanding requirements of each bandwidth. Each are consistent. Thanks for attention.